Personal finance practice problem using OneNote. Present value and future value calculations with the help and use of tables. Let's talk finance, and this time it's personal finance. Here we are in OneNote. If you have access to OneNote, would like to follow along, you're not required to, but if would like to, we're in the icon on the left-hand side. We're in the Practice Problems tab down in the 1122 Present Value and Future Value Tables Problem 3 tab. Also note, when using OneNote, look at the Immersive Reader tool. Our presentations will also be in the text area, same name, same number, but with transcripts. Transcripts that can be translated into multiple different languages and either listened to or read in them. Closing the icon, we got our information up top, calculations on down below, looking at present and future value calculations, focusing in on the calculation format of the use of tables. But before we do, let's see what we've done in prior presentations. Not that you need to have seen the prior presentations in order to see this presentation, but in order to see the multiple ways that we can do the same calculation with different methods so that we can choose the best method to use in a particular situation and be able to understand and follow other people if they use other methods. So our information up top says the yearly earnings percent in a savings account is 18%. Therefore, we're going to be assuming that there's going to be an increase of 18% annually on the savings account. That's a high rate for a savings account, but we could apply the same principle and concept to any type of investment, whether it be stocks, whether it be a home, whether it be land, a CD, savings account, and so on. And we use some other rates in prior practice problems, so we want to jump up the rate to 18% here. And the question then is, how long will it take for the account to double, which we can find without even having an investment amount by using the rule of 72. So we could then take 72 divided by the 18%, or 18 would give us the 4, not the 18%, but we're using the 18% to determine 18 to get 4 years. So the approximate time period that we expect it to be doubling if we have an 18% annual increase would be then 4 years. Now we're going to assume then a number of 3,000 as the initial investment. If a problem does not give you the initial investment and you want to guess an initial investment or pick an initial investment to make it more concrete in your mind, you might want to choose 1,100 or 10,000 or something like that. We're going to use 3,000 here because we used 1,000 in the prior practice problem, just to show that we could pick basically any initial investment and any starting point and apply these concepts to them. So that would mean that we would assume that in 4 years about, that 3,000 would double to 6,000. Now then we ran our tables down below. So we ran this with the tables and having our periods on the left-hand side. The table is quite useful to give us a running balance so that we can actually see what is happening with regards to the interest. We could see how it is increasing and compounding over time and the impact then on the investment line. So we're in between years 4 and 5 at the point at which it's going to be increasing or doubling from 3,000 to 6,000, noting that, of course, it's a little bit over 4 years. It's not exactly 4 years, a little bit over 4 years there. Then we have the same calculations that we used with the present and future value, as well as the number of periods functions in Excel, which is a bit more exact. Whether we use the future value, the present value, or the number of periods, we come up to the same result of that 4.19, which is the time period between which, or how long it would take for the present value to get to the future value. These formulas being related, and this is going to be similar to what we will do when we go to the table. So we want to emphasize it here while we have these kind of lined up next to each other. Note that whether we use the tables, whether we use the calculations, or whether we use these Excel formulas, when you're thinking about a present value calculation, you're typically thinking that the end result will be the present value of the 3,000. And what you're going to need for the calculation will be the future value, which in this case we know to be 6,000. So we're going to take the 6,000, discount it back using the rate to get to the 3,000. The thing that is unknown here is the number of periods, or the distance of time between the two, which we solved for here using a goal-seek method to be 4.19. Then if we use the future value, we could see this the other way. This would mean that we're getting an end result, which would be 6,000 at the end of the formula. And we would need within the formula to include the fact that we'd have the present value of 3,000 at kind of the starting point and trying to project where we'd be at the end into the future. And in this case, doubling. So we know what that would be. That would be the 6,000 at the end. And we would then use the rate in order to basically do the compounding of the 18%. The unknown here also being the number of periods. Then we have a more direct method that we could use in the functions, which would be solving for the number of periods, which would be similar to us if using an Excel formula, as we do down here, to be taking this formula and then solving for n and finding the answer with n. Now, when we go down to the tables, then we're going to have a similar situation where we have the present value and future value kind of components. That's how we typically use the table. We don't typically have a table solving for n. So we can't do that kind of method in a similar way. It's that we might use the present and future values in the functions. So then the question is, well, how do I use the tables in order to figure out n, the number of periods, when depending on the table's designed to multiply something by the amount on the table to get either the present value or the future value. And that's a common way, or this is a kind of a twist that many times a book problem will use to force you to use the tables in a bit of a different way. And note that when you're using tables, that's usually going to be something that's going to happen when you're in a school setting. Because if you're in practice, you'll probably have access to an Excel worksheet if you're doing something as complicated as time value of money would indicate that you would need to be doing, and you'd want to use Excel or a financial calculator. In a school setting, they will try to take away your financial calculator possibly, but still want to make it a bit easier for you to do the calculations if you have more complex calculations. So they might then use the tables, which, as we will see, has limitations. And therefore, if you know those limitations, then you can kind of get an idea of what types of problems you might be seeing when you're going to be using those tables. So if we scroll down, then we're going to say that 4 tables that we have, and I won't show the 4 tables, but just note that there's 4 tables that you want to keep in mind. There are 2 present value tables and 2 future value tables that you want to keep in mind. And each of those categories have 1 annuity table, which represents a series of payments, and 1 non-annuity table, or a 1 value table, which is a non-annuity table, has 1 payment that's either future or present value. So in other words, on the present value side, you've got an annuity present value table, which has a series of payments, and a non-annuity present value table, or present value of 1, it's sometimes called. And on the future value side, you have a future value annuity table, series of payments, and future value of 1 table as well. And we'll be using the non-annuity tables both on the present value and future value. And note, again, we don't have a table solving for n, so we're going to kind of back into that number. So let's first look at this present value table where we have the rates up top on the top column. We have the periods on the left column. So the rates represent yearly rates typically, or they don't necessarily have to represent yearly rates, but in other words, when you hear a rate, usually it is a yearly rate unless they tell you otherwise. And the periods in our case are going to be annual periods, but they don't necessarily have to be. So in other words, if you're dealing with something that's compounding monthly or semi-monthly, as is the case sometimes with bonds, then you're going to have periods over here that these numbers could represent something other than years, like half years, 6 months, or months. But if that is the case, you got to make sure that you have the corresponding rate that you're looking for up top. And that means that you're going to have to take the yearly rate if it's going to be a 6-month thing and divide it by 2 for 6 months, or the yearly rate divided by 12 to get the monthly rate. And when you do that, you will end up with uneven rates and rates that are quite small. So some book problems will give you periods other than years, but if they're going to force you to use tables, they will often use years because that'll make the rates more constant. Note the table's limitations, as we'll see here, do not have basically percent or decimal points on their percents. They got to use kind of like even percents, and they got to use even periods. So when you have uneven periods, it becomes more difficult to use a table, although Excel can handle that quite easily, and it's not a problem. So if you're forced to use tables, you can expect to see those nice even problems that aren't really practical in real life because they're forcing you to kind of use a table oftentimes. So that's what you would kind of expect. Now, this problem highlights an indication of a problem we have here with this 18%. Note that 18% is on the high end here, and at the high end, they start skipping numbers, and there is no 18%. So this particular problem, a book problem, may still give you a problem like this and try to tell you to use the table to estimate it, but it's more likely oftentimes that a book problem will give you a problem that fits nicely into the framework of the table with the limitations that will be included in it. So that's just to highlight, some of the difficulties or problems with the table. Now, a present value table, normally you would have a future value amount, which in this case we would imagine like 6,000, double the starting point, the ending point. We'd need to multiply that times something to get back to the present value of 3,000. So in this case, we would have it. It's got to go in half because we're starting at the endpoint future value, getting back to the starting point, which is half of it. So we would expect the number in the middle here to be 0.5. 0.5. So what we're going to do is say, okay, I don't have 18%. I'm going to look for the percents up top, somewhere between 16 and 20, and then find the corresponding period to get an approximation of how long it would be with the use of the tables. So if I use the 16 and say, okay, I'm going to go down on the 16 until we get to a 0.5. It looks like it happens somewhere between year 3 and year 4. Right, somewhere between year 3 and year 4, we go from 0.6575 to 0.5714, and then that's 16. If I go to 16, it's 0.6407 to 0.5523, and then if I go to 20, then it happens sometime between year 3 and year 4, and if I go to 16, it happens sometime between year 4 and year 5. So if I look at the difference between those two, I'd say, it's around somewhere between 3 and 5. It looks like it's around 4 years, right? Which is actually the approximate answer, around 4 years. So again, you can see the extreme limitations of the table here to use it in this way. Although again, a book problem might force you to do it, given the fact that you've got uneven decimal numbers over here, uneven periods on the left-hand side, and because the interest rate is fairly high, the tables don't have all the interest rates. If I was to do that same kind of approximation on the future value table, this is a future value table, which normally we would thinking we're going to start at the present value now, 3,000, get to the future value, which is going to be double the 3,000 or 6,000, and see what we would need to get there. How would we get there? Well, we would have to multiply the 3,000 times 2 to get there. So I'm looking for something with a 2 in it. Once again, I'm limited because there's no 18% column. I've got 16 and then it jumps up to 20. So if I look at the 16 column, you've got between period 4 and period 5 that it goes from 1.8106 to 2.1003. And then if I look at the 20 column, it happens somewhere between 3 and 4. So again, you'd think it's somewhere around 4 years that you'd have to basically estimate. And if you're imagining a multiple choice question, you can imagine them giving an estimate that would kind of work between that, right? Somewhere between 3 to 5 or 4 to, they can give you a range. And even with an imperfect problem like this, kind of force you to back into the best answer with a table kind of calculation. But also note that they can also use tables to give you an answer because the tables round to 4 digits. So if they want to force you to use the table and try to prove to themselves that you're not cheating in their eyes with a calculator, then they can make the answer tie out to the rounding difference, which would be usually irrelevant in normal practice problems or in real life. But, they can differentiate their answers on a multiple choice question based on the rounding to determine whether or not you pick the right answer with the format of the table that they use. And we might take a look at that in more detail in future presentations.